Welcome to a new test and teardown video. This time I think it's something completely different. It's an MGE UPS Systems PowerStar II. So it's a UPS obviously, but this one is capable of delivering 16 to 17 amps. 230 volts AC. So that is, I think they say 2,400 watts and 4,000 VA. Here at the front panel, we can see the PowerStar II, manufactured for IBM, so it's clearly for a server system. We can see some different LEDs, and everything is of course software controlled, and that is more or less all I can see here at the front. Let's look at the rear panel. That is some heavy thing. That's why I'm losing my breath here. It was 20.6 kilos, so yeah, that is something. I think this one uses external batteries. It is just a single phase output. There is a nice connector for the output right here. And this is a little external add-on for those connectors, as you can see here. Oh yeah, there's a little label right here where we can see, let's see if we can see this. The specific, this is so much out of focus, I'm sorry about that. The battery is 120 volts, 7 amps. So that means it's 10 of the 12 volt batteries in series. And you lift this and then you access the external battery connector. And that looks a little bit like this. I don't know exactly why we got that many. Maybe they are connected in banks or something like that. So when they go into this unit, this is when they become a serious connection. Let's try and look a little bit about how deep this thing is. Because if I take the entire unit and the breakout panel here, I think it's 63 centimeters deep. And 45 centimeters high, so yeah, that's definitely something. I really like this breakout panel here. It says it was tested in 2000, so that's 24 years ago. And it fits really nice here on this output connector. You know, I'm definitely trying to see if I can figure out how to open this. I think it's gonna happen. Oh, I need some more hands. I'm a little surprised to find it is actually running with internal batteries. Of course they are not mounted, because then I wouldn't be able to lift this thing. But we got all the cables to do the connections here of the 10 batteries in series, and then this will be the entry. It looks like it is heavily corroded. See, all here, yeah, it's completely rusted and super dangerous to try and power this up. So I think I'm not going to power it up, but it's definitely not going to prevent me from taking a little bit more apart to enjoy all the fantastic internal parts. This is some fascinating construction. I mean, everything in this one is made so nice and beautiful. It's not at all like a regular UPS, but bigger. Oh no, they went all the way to make it as nice and fantastic as possible. We even got a big controller circuit board up there. I'll have to take that one out so we can inspect what is going on. But let's just focus on the first board here, because I feel we got the DC voltage coming in here, and it goes in and out here. We got some main breaker with a current protection. So it's an auto fuse, and then power goes in here. Those two big hefty fuses. And then I think voltage goes through this big inductor and it goes back. I haven't yet figured out exactly how this goes back, but it looks like, here we go. So it's just a filter choke or something like that, right? And then we go in here and there's a relay right there. And then this is just a big common mode filter. And then there's a big switch mode section with quite a lot of big transistors. And again, on the other side, and that will be drivers and current sensing and all that kind of stuff. What is that? Yeah, this is a trigger transformer for driving some of those transistors. And on the other side here, we got also gate drivers and another little trigger transformer and power supply transformer for all that, up to couplers and whatnot. This is the flat cable that goes to the controller board. Another funny thing about the high power interconnect, how they're doing this, look at those two right there. So they connect to those big hefty brass screws like that, and it's the same here. All those VS to go to the other side, and then it's probably connecting somewhere here or over there, right? And all those capacitors to handle the ripple current. And there you have it. Now you're connected to this side, and you go in to some resistors, and again a big, oh, I really need some more light, but it looks a little bit like it's the same sort of section right here. And then there's another power transformer here. Can this really do like 2,500 watts? And that is just a little local power supply and another mains transformer for local power supplying. And how many fuses can we find in this one? All those fuses, and another one, and another one right there. And on this one, there's also a fuse here. So they're really afraid of blowing up stuff, and of course preventing fire and all sorts of bad stuff. Yeah, that's also trigger transformers for all the gate driving we have here. Yeah, I think I'll try and take a little bit more apart here so we can see what's going on. So from this angle we can better see the transistors, diodes, and 4 transistors in there. I really like the transistor mounting. That is a very brilliant idea. And those capacitors, they're 400 volt. Why is this always out of focus? And let me try. This is super heavy. 2 transistors and 4 diodes. So exactly how this is done. Yeah, all those are in parallel. All the 400 volts capacitors. And yeah, that will be the transistors and some more transistors. All okay, they're in parallel. Okay, and down there we got a parallel set, and again here. So they're definitely trying to push up the battery voltage first to a higher voltage, and then they will chop this into the output voltage. So I'm still trying to dig my way into that other board here. I just find a lot of cool things. So there's another little local fan in here. And see what they tried to make all the air from that fan goes straight through this one. And then there's of course another one right here that will feed a lot of air through that other fan tunnel system that is right there. So there's another hidden connector right there, and it was sealed or hidden like that. So this is I think this is the main external battery connector, and there's also power in and out with some big hefty cables like that. But then there's also a thinner set of wires, and those also goes to the other ones, or two different sets. So I think, this is just a guess, it could be a temperature sensor in the battery system, so we can have two different sizes of external or systems. I mean, this is probably just another model of battery, and now this model uses another connector. Is it another size, right? And so that is more or less what I've found out, and I still cannot get this circuit board out because everything here is in the way. And they welded this bracket to the chassis, preventing me from taking this out. I don't know how that is supposed to be. I will have to think a little bit more. Of course, we got some bolts down there. And chassis is also mounted using two different sets of bolts. I mean, the self-tapping and... Why so many different bolts and systems here? I mean, you need different tools as well. I am having a little bit of a fight to get the main circuit board out. So far they're using 3 different screws. I should probably show you some of the different screws they're using. So this means you need 3 different tools for assembly and for removing. I mean, why would anybody do that? But anyway, the inductors. Look at that big, beautiful inductor here, and the air gap reveals we have an inductor that is supposed to be used with a very high DC current content, and that is why you have this air gap, so you prevent it from going into saturation. Obviously, this also costs a lot of inductance, but that is a pretty good trade-off. Once you have saturation, you don't have an inductor. So here is a potential problem, a reliability and quality issue. I really want you to see here what is going on. This is the earth, and I don't know if you can see the thin plastic isolation here. 1 layer of isolation. If you push this in exactly like they did, see, it is actually touching the metal to the chassis like that. So it's really easy to imagine it can go through over time and when it gets hot and all that. So that is not so good. I didn't see the same problem with the output connector. See, they are nice and fine and they go all the way in correctly. But here there's a problem with the mains filter in here. There's a little metal box with the filter right there. So this is the mains in out filter section. And of course they made some really nice common mode chokes and some capacitors to chassis and all that. But there's another little funny thing. The battery power that went from the bottom here into through this switch. We also had this big ferrite that you saw in the way for the automatic fuse. And then they added this tiny little board with some extra capacitors to chassis. I wonder why they did that. To just get barely below the EMC emission level. That is obviously why. So I was able to get the main controller board out, and that will be the LEDs and the little push button board. The fun thing is there isn't any connectors here, so that's just a flat cable with these solder in. And this is a 1.27 spacing, so that is quite cool. I could use these for some other designs, and I really like there's a flat one and then there's a straight one. I kind of like that. Really neat. And the controller board here is really full of electronics, and date code is 97. See if we can check it out. All those discretes and gates for doing this and that. And then we have the big fat microcontroller here, running at 16 megahertz. And yeah, that'll just be some more logic. Tons of logic. Really, why? It's software controlled and all that, right? And then some little power supplies, input, output, different serial interfaces for all sorts of stuff. Yeah, this looks like an Ethernet, but I think it's just serial. I don't really see anything like that. There's a room for a little simple switcher right there. You see the little 5 pins, diodes, inductor, capacitors, and voltage set up here. So, and a little linear local regulator and optocouplers. Pretty neat design. It's a multi-layer board, and it's a 4 layers. See, we got these nice layer indicators. I don't have any components on the bottom, so it's a single component. Oh, look at that. Isolation distances in the internal layers. Really? Somebody misunderstood their isolation requirements, because the internal layers, you don't have this kind of crazy requirement for isolation distances. So that is a little bit funny. It's only outside copper, because you can see here the solder mask isn't that super good as the internal layer isolation is. But it's still funny to see when they probably had an argument about isolation distances, and then the designer said, okay, fuck it, I just put it all the way up and then be done with all those arguments. I know I have these arguments with some people, you know. Well, that is a beautiful controller board. Let's look a little bit more on the main output board. This is, of course, the output board. The other one we saw, that is this is the output board, and the other one was the input regulator. This UPS consists of 2 regulators, right? So this one generates the output waveform, And we just have the most crazy components here. I mean, look at the size for this inductor here. I can only reach halfway around this toroid. And this is a relay, 20 amp relay. We've got some smaller relays right there. I don't know if I can see the part numbers. No, not there on the other side. Current sense transformers. The two wires you see that goes through them, they're just in parallel. This is just to split the current to each of these. And also there's a maximum current per soldering, per wiring, per the way that this is all done. So by doing it this way, they can handle all that current. And again, another one of those massive inductors. Should probably try and remove one of those transistor mounts. I really love the way that this is done. It presses in the center of the hottest place. Instead of using, let me try and do that. So instead of using the hole, why can't this just go away? Come on, man. So by using, if you're using the hole, you're pressing up here, and then there isn't a lot of pressure down here, where this is the hottest area. This is where the chip is inside. So they're pressing exactly where the chip is. Also, they are not causing isolation issues, because you can imagine this is connected to chassis or some ground or something like that, right? And everything here is on live voltage. And this way we have that many millimeters to anything metal or to anything live. It's really, really a good way with isolation, but also definitely the best way, best thermal way. So you can run those transistors at higher currents. Of course, you need these really neat, specially designed parts. Oh, they're also made nice and round down there. They thought about everything. I love it. They're nice and yeah, they're quite massive aluminium part. Brilliant design. Oh yeah, about the fuses here. So that will be some 30 amp fuses, but look at that. They are silver plated for good contact. But look at that, the silver corrodes and becomes completely dark. That will be some really powerful MOSFETs and all the diodes. And we also got on the other side some diodes and MOSFETs again here on the step up board with the big capacitors. But there's just one tiny little thing I want to show you. I found pretty funny. Look at all those resistors here. Instead of using a power resistor, they used tiny little resistors, and I don't know if you can see this, but they are just connected first in series and then in parallel. Let's look at the other side of that area. Definitely. Isn't that funny? I think it's also a nice way to make it flat and compact and all that. And they repeat this. So there's another little space here. Look at those in the middle of the picture. You can see there's a track connecting to 6 solder points, right? Yeah, and you also see the nasty corrosion. This completely defect. This is of course why it was thrown out, is because it's completely dead. but it's still fun to see how it was made. You can see the isolation here and all that kind of stuff. But okay, let's get back to those resistors. And here we go. Parallel resistors, 1/4 watt each. Isn't that funny? I also see when somebody tried to put in this screw, they were fighting and fighting until they finally hit the hole. So you got those funky scratch marks. Anyway, I think this is all I wanted to show you in this video about this UPS. So thank you very much for watching. Bye bye. See you soon.